I better be listening, you guys that have more experience, you know, just to learn a little bit more. The fun part is to learn, right? So this is, yeah, let's see how
Well, now you just stole my words.
Okay, I stole your introduction. Sorry, I stole your introduction. So yeah, maybe Ivan is lost somewhere over there because you know the conference or you know, chatting with someone. So I will send a message to him. Okay, we still have 4 minutes. Okay. So you are also planning, relying somebody, that was my plan. Okay, us that is Zora, Leandro, Ivo over there. I'm just waiting, you know, because you make some question here and there, some comments, but seems that you are relying the same approach, Leandro. Just
Yeah, me. I'm
no,
still looking up to you.
Yeah.
After all these years.
After all these years, yeah. Yeah, since 1983, I started on power electronics on 83. So I have witnessed, you know, something. But
it's been a while, I guess.
Yeah, I think I'm getting, you know, it's tough to get somebody that is older than me on the business. But so this is, I'm not saying this is good. No, I had to be more young, you know, with the same knowledge, man, but younger, you know. More energy.
I'm 3 years behind actually. 1996.
1996. No, I mean yes. 80. I started.
Oh my 80, God! Oh 80, my God! Sorry.
Yeah, 80 something. 84 actually.
84. Okay.
The first transistor that I blew was a bipolar transistor from Motorola. You know.
Well, it takes some effort to blow it up.
No, today it's hard to blow a transistor, but those days, my friend, I had nightmare on those those transistors. So it was actually it was expensive. It was difficult to get, and then we have to have care. And then the technology was not that good. It was bipolar junction transistor, 300 volts, 200 amps, bipolar junction transistors. And then he required a huge driver, you know, because you need a lot of current. The gain, the current gain was very small. So the driver, you know, the circuit driver was kind of complex and expensive. Anyway.
But you still remember?
Of course.
The first one.
It's the first transistor that.
Is it just me or we lost connection?
I learned the hard way that commutations losses should be taken into account seriously, you know. So I was working with one converter. It was 5 kilohertz, I remember. It was making a noise.
Nice noise.
No, horrible noise, you know? And then I said, "Oh, this is." And then I had this. The carrier was set by a generator, Hiva. We are just killing some time here. We're waiting for you.
Yeah, so I'll kill the discussion now. Yeah, so now the boring guy joins and then everything dies. Huh?
No, I was telling just how I blew my first transistor back in the 80s, you know, but anyway, that's not important. Anyway, and then I started to dial that frequency of the carrier, and then the noise becomes nice after 20 kilohertz. I said, okay, everything's solved. And then didn't take long that everything turned blue, you know. Anyway, okay, let's start our discussion today.
So let's start because we are on time right now. So we are already live on YouTube and on the platform. So first of all, I would like to thank all the attendees again for joining us in this panel discussion, the first panel discussion of SEPOC 2021. And for this, we have this great team. here with us. We have again Dr. Ivan Solanovic from Typhoon that is joining us after his plenary talk, right before the panel discussion. We also have with us Dr. Zoran Miletic from the Austrian Institute of Technology, Dr.
Hello.
Leandro Della Flora from DEMFOS, and Professor Humberto Pinheiro from UFSM. So thank you very much for attending this panel discussion and being with us in this event. And I hope that we can have some great talks and learn a lot from you guys. So first of all, I would like to introduce our panelists. And I have already introduced Dr. Ivan Solanovic on the plenary session before, so I will skip him now. But let's start with Dr. Zoran Miletic, who is farther away from us. And so I will read his biography and then we can move on. So Dr. Zoran Miletic received a Master in Science degree in Electrical Engineering at University of Belgrade, Faculty of Electrical Engineering in Serbia in 1996, and Professional Certificate in Power Electronics from the University of Colorado at Boulder, Department of Electrical and Computer Engineering, USA, in 2008. For almost 2 decades, he has been leading product development for power electronics converters for renewable energy applications at Centrex Technology in Canada and Schneider Electric Solar, Europe and Canada. Since 2014, he has been with AIT, the Austrian Institute of Technology, as Senior Research Engineer. His experience includes the design of power electronics and control methods for solar MPPT charge controllers and single and three-phase solar inverters from few kilowatts to several hundreds of kVAs. His current research interests are control of grid-connected and grid-forming power converters in microgrids and hybrid DC and AC grids, novel multi-level and multi-cell topologies for power quality applications, and Hill simulations and modeling. He is an IEEE senior member and holder of several US and international. I will also read the biography of Leandro Della Flora. So Leandro Della Flora received a bachelor, master and doctor degrees in electrical engineering from the Federal University of Santa Maria in Brazil in 2003, 2005, and 2009, respectively. He joined DEMFOS in 2011 as control systems engineer in the high power motor drives division located in the USA, where he has been applying power electronics and motor drive technology in a variety of product development projects, including medium voltage adjustable speed drives and high power solar inverters. Prior to coming to DEMFOS, he was a professor in electrical engineering at the Federal Technological University of Paraná in Brazil from 2009 to 2011. He also pursued a system engineering position from 2014 to 2016 at UTC Aerospace Systems, now Collins Aerospace, where he worked on the development of high-fidelity simulation models for electrical actuation systems used in aerospace applications. So also again, thank you very much, Leandro, for joining us. And now Professor Humberto Pinheiro.
Thank you.
So Professor Humberto Pinheiro received the bachelor degree from Federal University of Santa Maria, Brazil in 1983, the master in engineering degree from the Federal University of Santa Catarina, Florianópolis, Brazil in 1987, and the PhD degree from Concordia University in Montreal, Canada in 1999. From 1987 to 1999, he was a research engineer with a Brazilian UPS company and professor with the Pontifícia Universidade Católica do Rio Grande do Sul in Porto Alegre, Brazil, where he lectured on power electronics. Since 1991, he has been with UFSM. His research interests include modulation and control of static converters, especially those used for the connection of DER to the electric grid. Dr. Pinheiro has published more than 80 journal papers and has supervised more than 10 PhD students. Dr. Pinheiro is a member of the IEEE Power Electronics and Industrial Electronics Societies. Well, thank you, Professor Humberto, for joining us also. And now we can proceed to the panel discussion. And for that, I will invite each one of the panelists to present a short presentation with their overviews on the subject of this panel discussion. And then we can move on to a session of Q&A. So I really encourage the participants, the attendees, to ask questions. You can ask questions through the Zoom chat. You can ask questions from the YouTube chat. And as we have 4 guests in this panel discussion, you can ask a question for everybody to answer, or you can ask a question for a specific guest. So please feel free to ask as many questions as you wish on this panel discussion. So again, as Dr. Ivan has already presented his speech on the plenary session earlier on, I will kindly invite first Dr. Zoran Miletic to begin his presentation, as he is farther away from us in Europe. So let's begin with you. Please feel free to join your presentation and share with us what you have for us today.
Thank you so much for a kind introduction, and I'll share my presentation. Today, my presentation will rather be very short. It will just cover research topics that are conducted at Austrian Institute of Technology in Vienna, and with emphasis on challenges in our research. As far as applied research topics, first of all, let me mention that in Austrian Institute of Technology in Power Electronics Group, we have academic, more fundamental power electronics research topics, as well as applied research topics. Applied research topics are closer to, let's say, industrial applications, as opposed to more academic research topics, which are focusing on, let's say, near future or future applications, as well in industry at the end. One of the key research topics in our group is control of grid-connected converters for grid code compliance and for grid with grid disturbances. In general, control of grid-connected converters should be suitable to support required grid functions according to grid codes. And the biggest challenge there is that grid codes are actually moving targets. They're not solid, they're not harmonized across the world, and they're evolving and changing all the time. And they're very well understood, but until next revision or next change, and then it is becoming even more complex and challenging. As far as grid disturbances, our focus is on two topics: voltage unbalance and current imbalance. And for that, we are focusing our research on a special type of control, which includes positive, negative, and zero sequence rotating current reference frame controllers. And in this research, we face challenges such as power oscillations or loss of energy harvest and some reliability issues caused by voltage imbalance or current balancers. Next topic that we cover in our applied research are grid forming converters in low inertia microgrid and hybrid AC-DC applications. And as far as GFC, our grid forming converters, we are focusing on DRUP, VSM, and matching control and virtual oscillators. And in AC-DC hybrid applications on active front end with DC DRUP. Biggest challenge in, let's say, microgrid applications with low inertia and hybrid AC-DC applications that we see at the moment are lack of inertia and lack of short circuit capacity of these grids. And finally, in the last couple of years, we're also focusing on novel multi-level, multi-cell topology with the aim to revisit this field again. With the aim to achieve ultra-high volumetric power density and ultra-high efficiency over 99.2%, and to actually, by doing so, reduce losses so much that we won't need heatsink or any, let's say, active or passive a special cooling effort. The issue there is complexity of control, and I'll have a slide in addition to elaborate on that as well. In the following slide, I'm just showing some of the issues that I mentioned regarding voltage unbalance. Here's an example of, let's say, state-of-the-art three-phase PV synchronous reference frame control under unbalanced grid conditions. Due to unbalance in PV applications, we see here that MPP tracker is not able to harvest and transfer maximum power available from PV array. Then inverter itself may exhibit higher currents that can overload inverter and potentially cause inverter to trip, and oscillations or presence of a second harmonic in DC bus. As a result, effective DC bus voltage range gets reduced. With advanced control methods that we have investigated and developed at AIT, which is based on decoupled dual synchronous reference frame control, there is these challenges are being addressed at the end, and PV inverter with this type of control is able to actually harvest maximum power and to mitigate risk of tripping and eliminate active power oscillations, and therefore also that does not reduce effective DC bus voltage range. What we are showing here is AIT Smart Grid Converter. This is our flagship product. This converter is 4-phase converter. One unique feature of this converter is that it's able to handle unbalanced grid conditions and load imbalance. You can see in the time diagram here that let's say currents are heavily they're sinusoidal, but they're not symmetrical. They're literally almost all pointing in one direction. And under normal conditions with three-phase converters, this type of currents are causing severe presence of second harmonic. This second harmonic is with 4-phase control, special 4-phase control entirely reduced, which is pointed here. And as a result, DC bus volt is much smaller, second harmonic is eliminated, and operational DC voltage range is wider than standard three-phase converter. As far as novel multi-level, multi-cell topologies, on the left side we see normalized trade-off curve, which is showing typical 2-level, 3-level, and 5-level, in this case A and PC topology. And as we took several, let's say, criteria or requirements to analyze, and which is very clear that 3-level topology, which is, let's say, industry flagship topology in many applications, seems like a clear winner. But if we want to actually further reduce size of converter, we can do that by reducing filter inductance, for example, or by eliminating losses. And then we arrive to the 5-level topology, for example, which on the other end has its own challenges, such as increase of number of semiconductor devices, gates, and apparently more devices through which current is flowing, which at the end does not result to a higher conduction losses, but it's just to show this problem. And on the right side, you can see a topology of our interest that we are investigating. It's so-called 5-level NE type, which is comprised of standard 3-level T-type and 2-level stacked flying cells, which is at the end evolve in the topology which is shown on the bottom, which is currently under investigation. And with this topology, we believe that we can reach efficiencies over 99.2%, not only peak, but overall range. And this is with all silicon semiconductor devices. Why are we looking at multi-level, multi-cell topologies? We are doing so in order to address certain applications such as integrated motor drives and also power quality applications where size and volume is critical, and where if we can eliminate entirely heatsink or use existing enclosure as a heatsink because of the higher efficiency, this might be possible at the expense of higher complexity of gate driving and control in general. Well, in all these applications, our enabling tool is HIL, or hardware-in-the-loop simulation, and we use hardware-in-the-loop simulation for all kinds of applications, for development, for test, validation, pre-certification, and a lot more. And what is shown on the left side is a typical setup that we use here at AIT, which is comprised of Typhoon Hill real-time simulators and our controllers, so-called AIT Hill controllers, which are bundled up here, for example, for a typical microgrid C-Hill test stand, high fidelity microgrid C-Hill test stand. In addition to research, we also offer design services. This is just a slide to mention that we do a work for industry, in this case for Siemens, Atos. This was, let's say, space application. Thank you. That was all from my end.
Thank you very much for your presentation. And now we move on to Leandro de la Flora. You can share your slides and make your presentation.
Sure, thank you. Let me share my screen first. Please let me know when you can see it.
Yes, we can see it.
Perfect. Okay, so I first of all, thank you very much for this invitation. It's the first time that I've been in touch with the university in almost a decade, and it's certainly an honor for me to be participating in the seminar. The university, I still bring it in my heart. I mean, spent there more than 10 years of my academic formation, and I'm very glad to be having the opportunity to share a little bit of my experience that I acquired after leaving the university. So I bet there are many students in the audience, so I'll try to share the best I can. Of course, still protecting some of the critical proprietary information of my employer. But you guys feel free to make questions at any point. The slides that I prepared are coming more from the marketing group. It's really more about introducing or giving people an overview of the products that we are developing in this particular division where I work, which is the medium voltage motor drives, high power motor drives in the US. The emphasis has been dealing with motor drives for more than 50 years, and most of the development happens in Europe, but for high power low voltage drives and high power medium voltage drives, the main design center has been in the US. In my case, the medium voltage drives, they are developed here in North Carolina, and they are named vacuum 3000. The reason vacuum is because Danfoss has acquired Vacuum, which was another motor drives manufacturing company. Danfoss has acquired this company back in 2014, and this product started to be developed by Vacuum earlier last decade, and Danfoss has kept the name Vacuum 3000 in honor of the good work that has been done since the beginning. And basically, here we are talking about drives that are going or are offered in power ratings from 2 megawatt up to 7 megawatt. And the idea is to make them easy for the system integrator or the final user to build, to assemble, and to integrate with their applications. So these drives, they are basically offered in two main variations. One is the drive kit, which basically means we sell these products as parts, individual parts to the customer, which can decide how to assemble or build a drive in their own application. And that gives them a lot of flexibility, because instead of purchasing a cabinet, that's what we call enclosed drive, they can build the system to fit the exact, let's say, physical needs in terms of footprint of the drive to meet their expectations. And of course, the company also offers the traditional enclosed drives, which is basically a cabinet that has everything inside the cabinet, including the power section and controls. And this slide is basically showing some of the offerings that we have today. Like I said before, the rated power starts at 2 megawatt or 2 MVA and goes all the way up to 7 MVA. So what you guys can see here on the left side is one example of one of these drives. This is the smallest frame size, which is a 2 megawatt drive, and it's extremely compact, and that brings a lot of value for the customer. And when you say medium voltage, what does that mean specifically? It means that voltage levels are 3.3 kilovolts or 4.16 kilovolts. And these drives can operate on 50 hertz or 60 hertz grid, depending on what the customer needs. And another thing that is offered is the front end of the drive. We offer the traditional diode front end, which means we have an uncontrolled rectifier on the input section, and of course a filter to mitigate harmonics. But we also offer the active front end rectifier, meaning that it's basically a three-phase inverter that's mirroring the output of the drive. So it's really producing very low harmonics, and it's helping the grid to some extent. And these drives, they are mainly in, let's call it, heavy-duty applications or very high-power applications in oil and gas, mining, marine industries. And we have sold them mainly for customers in the US and in Europe, also some in Asia. And of course, these products are they are still under development, meaning we have goals to reach higher levels of power. The highest we can provide today, 7 megawatt, but very soon we will be offering also 11 megawatt drives. And still the design is extremely compact, because we allow to take lower power drives and combine them in parallel. Inputs are connected in parallel, outputs are connected in parallel in a way that the customer can still control them as a single drive, meaning just one control unit that's acting upon all the power states, and still be able to have these very high power applications. So now I would like to steer the presentation a little bit towards the topic of this discussion or this panel today, because my understanding is we, or the audience, wants us to talk about how we test power converters to be integrated with distributed energy resources. And I think that that has everything to do with what we, or the challenge that we face in this industry, because testing means everything to us. We cannot deliver something to the customer that we have not validated yet, or at least that we do not have a high level of confidence. But the biggest challenge is we are talking about multi-megawatt drives, which are not easy to build test beds or test bays that will support the exact need of the customer. Meaning, I can tell by my own experience that in all these years, there hasn't been a case where we could basically repeat the same design to the customer, because in very high power, all that they want is customization. They want their needs first, and that means we have to accommodate their needs. We have to make a drive that's flexible enough. But when it comes to testing, that's the real challenge, because we cannot replicate everything that the customer wants, because that's a huge investment. And like I said, it's probably not repeatable so much. So if the company were to choose this approach of, yeah, let's build a test setup for each and every customer, what they exactly demand, we would be out of business, because this equipment is, the infrastructure that we have to build to support these drives is enormous. So what has been a game changer for us in this past decade is really the opportunity of using hardware in the loop simulations to integrate or fully develop our testing plans. And here in this picture, you have a picture of myself. We have lots of Typhoon Hill boxes, and here's just one example. In this cart, I am simulating a full AFE drive. Could be 2 megawatt, it could be 3 megawatt. But basically what it means is, in a single cart with the Typhoon Hill box, we are able to simulate a full drive with the main control electronics, main control cards that the actual drive has. And the Typhoon Hill box is basically doing for us the job that we would have to do in terms of creating the infrastructure so we can test the software. Because basically the software doesn't know if it's controlling the actual drive or a model in the Typhoon Hill system. And it was going to react the same way, doesn't matter what it's connected to. And that has been part of our development process in the past 3 years. I mean, using specifically the Typhoon technology, and that has helping us a lot to speed up the development. I mean, we are not replacing doing actual tests with a power circuit that's being fully exercised, but what we do basically is we take this intermediate step. I mean, in my case, since I'm a control systems developer, before I hit the lab, I want to make sure that the controller and the software are working together the way they're supposed to. And these tools, they are really enabling us to do that. I mean, we can build a system that mimics as close as possible what the customer wants, and we can test the software specifically. So it doesn't matter if the next step is going to be actual test lab or going to the customer sites and do a factory acceptance test. We have a lot more confidence now that the control will work as intended. But this is just part of the story. I don't want to extend this too much, and I'll be very glad to answer specific questions. I do have a lot of previous experience in the PV inverter business. I mean, until 2014, Danfoss was one of the major players in the PV inverter market. He has sold many gigawatts of power throughout the world. And my participation was on the high power side of these inverters, because in the US, what we did back in the day was we developed utility scale central inverters. And in this case, we're talking about converters that go from 1 megawatt to 1.5 megawatt connected to PV panels. And that was a very precious experience for me, because I had the opportunity to deal with many aspects of the design of the inverter. And one of them was really understanding the test requirements, the grid codes, and translating those requirements into our product and building the environment to test, to make sure that the software meets the expectations. So I'll be very glad to ask any questions regarding that. Thank you so much.
Thank you very much, Leandro, for your very nice presentation. And now, please, Professor Humberto, you can share your screen and begin your presentation.
Okay, let's see. Okay. Are you guys listening to me or not? Are you seeing the presentation? The first slide of presentation?
No, it's not showing.
It's not showing? Huh. Let's stop it again. Let's try it again. Okay, share. How about now?
Yes, now we can see it.
Okay, thank you very much, everyone, to have opportunity to share some thoughts with you guys about challenges and opportunity that we are seeing today. So I start by saying that we are experiencing a transformation. This is bring us opportunities to develop new things. Now we are saying that we are, witnessing this electrification of transportation, where electrical vehicles are becoming more popular, and replacing this internal combustion engine cars or trucks, whatever. So for one side, we see this wave coming of transformation, giving opportunity to develop inverters for the driving train, to chargers, to onboard charger, offboard charger, infrastructure to the electrification. So there is a lot of opportunity to power electronics engineer to develop new products. We see also from another side, we see this double three Ds, the decarbonization, digitalization, decentralization of the electric power system. So slowly the transformation is coming. So for instance, here in my house, I already have one PV solar generator. So if I look back 20 years ago, I wouldn't imagine that I would have this kind of PV system. So in addition to this, we see that there is a lot of data being generated from this system. And also the 5G is coming with the Internet of Things, okay? And new opportunities for business using tools like blockchain, as well as artificial intelligence to reduce cost of maintenance, for instance. So we see that from the broad perspective, there is a lot of things going on. So if I look back to the early of my career, I couldn't see a moment that where you have so many things going on at the same time. So we have the electrification of the transportation, we have smart grids coming, distributed generation, we have the environmental concern of the young generation are concerned about what's going on with the planet. So we have to reduce the emission of fossil fuel. Renewable energy is there as a possible solution for this mitigation of this problem. So in addition, there is this data. Understand there is a lot of data being generated, a lot of opportunity on this side as well. And then if you look specifically for the area that we are in, that is basically on power conversion, we see also nice things coming. So we see new semiconductor devices, we see wide band gap like silicon carbide, like gallium nitride. We see this brings new opportunities for designing new converters to make feasible new applications. So this is quite exciting as well. As Zora mentioned, so if you were narrow the problem to the reintegration of renewable energy to the grid, we have this grid code as moving target. So always evolving, you know, as the utility company are concerned with the integration of this new form of energy generation with inverters, they are changing the grid codes to make the to keep up with the reliability and of the grid. So the converter manufacturer also have to bring to the market as reliably as possible new products in this environment that is changing. Of course, the talk that I want to address here is basically regarding to control. So in order to put into the market this equipment, we need control currents, power, torque, whatever, you understand. So this is very challenging for the engineers. Okay, let's move on. So we have this motivation to increase the penetration of wind and solar, of levelized cost of energy is one of them. Of course, environmental impact is another one. So we see this a lot of deployments of wind farms, onshore, offshore, and also solar PV, both in terms of utility scale and residential scale. So in terms of connecting converters to the grid specifically, so there is a lot of functionalities that have to be introduced, frequency support, depending on the grid code that is being considered, so low voltage right through and so on. So there is a lot of operating conditions that one converter should be tested in order to satisfy all these alternatives. So in order to integrate this, as we see here, wind and solar to the grid, static converter is in the central of this. So if you considering the design of static converters, we have the selection of the semiconductor, the topology. There is a lot of alternatives in terms of topology. Thermal reliability design is very important. Also, EMI design is important. Controller design, of course, no one to want to a converter to run unstable in real life. In addition, we have to consider all the functionality associated with this for a given application. So there is a lot of things on the plate of power electronics engineering in order to put a product in the market. So we are discussing, I was discussing this with Eva back in 2016. And then we say, in terms of control, there is a lot of alternative. If you look to the IEEE Explorer, you see for grid-tied converter, there is 100,000 of papers with different alternatives. And then what comes to mind to one design engineer is which is the best choice, which is the one that I should select it in order to implement this specific controller for this application. So, and then we come up with the issue of comparison, fair comparison. How can we compare different strategy in a fair? So we focus on the problem of grid-tied converter. Let's pick up the case of grid-tied converter and see what we have inside and decide to make a course. So we join effort with Typhoon Hill and develop a course on controllers for grid-tied converters. So the idea is to give background on the controllers, synchronization algorithm, current controllers, and modulation and outer loops and primary controllers, and give a background. But in addition to this, provide a fair way to compare different controllers. Because if you read a paper, they always seems to try to sell the idea that their approach are the best one. Okay, no, so nobody wants to show the weakness of a specific controller. So the idea is to, so in this course, we have gather information from the theoretical side as a regular traditional design method is make analysis, transient analysis, steady state analysis, and then in addition we go through what we call test-driven design, that is extensive simulation, automated simulation with automatic report generation to compare different strategies. We divide in modules. The first module is the synchronization algorithm. So, and then the second one, current controllers, modulations, and then the last one is the primary control. So let's have a look of pick up some of the material that is available on Hill Academy. This is an open source, so you don't have to pay anything to run the simulation, to take the course, to get the certificate. And then also there is files available. So there is the source files are available. There is also Jupyter Notebook design files. So if you want to design an LCL filter for a grid connected converter, you are going to find there this script on Jupyter Notebook to design these filters, how to select this poles of resonant controller for the LCL filter controller design. You're going to find there, and then yeah, let's move on. Let's move on this. What we have here is, as I showed, there is in this course material you're going to find conventional small signal analysis for, in this case, for the PLL connected to a strong grid or weak grid, and also you're going to find the C language. Actually, in order, because we want to make this available for everyone. So not everyone has one Hill device available. So the idea here is to use a virtual Hill. So you're going to use the same environment for the simulation, but you are going to use this your own CPU, to run this. You don't have to have an external device. You don't have to make any investment in order to get familiarized and run these cases. And the C code also, the simulation files are also available in the site. So basically here is in terms of PLL. So once you have designed your controller, you want to test it. So it's also provide a script in Python to make hundreds or thousands of simulation and generate reports. So you have this. This is a color. Have a report in PDF file, and they have these colored tables. So of course, this fail and pass in the test. Sorry, fail and pass in test are associated with the thresholds that you have to set. Suppose maximal acceptable total harmonic distortion of the current of the grid side. So it's a parameter in this Python file. So you can set over here what is the maximal TGD that you accept. So if when the simulation that is run violated that one, it will be plotted as red, and then you can go there and have a look to see what's going on. So basically, what this script does, it automates the process of testing. So you of course you have to design the controller, you have to implement the controller. The test is already set over there, so you have to just change the parameters that you want to define as, and then you run the test. So you can have a coffee, go over there, wait a couple of, depending on how many tests are you running, it might take 10 minutes, it might take, depending on the machine, it can take even a couple of hours, and then you have the report, okay? So in this case, is showing the steady state error that is maximal acceptable is in terms of the synchronization, actually is the grid angular position that is accept 3 degrees for error in steady state between what you estimate and then what is the grid actual grid angular position. And we see here that under the fault, this is a type of fault. Fault A is a symmetrical fault, fault B, C, and D, and E. This fault E here, and when you have this depth of the fault, I don't remember exactly what is the amplitude of the fault. So it shows that the error is with this PLL that have been tested, these are both the threshold that you have specified. So the idea is that whenever the color is red, you can go there and then you check it to see if what's going on. So of course there is a lot of simulation that have been done. So the initial idea is that people, as it is an open source platform, the people pick up this the different PLLs, different current controllers, different primary controllers, and then they implement it and test it, and then they can put the result in this platform. Okay, so this is the idea is to make easy share of the information, and as well as a fair comparison, between different approaches. So here is another synchronization algorithm. They have a second order generalized integrator at the input that extract the positive sequence of the voltages at the point of connection, and then it outputs the frequency or angular position, probably frequency. It outputs the frequency and also the angular position. It outputs over here. So, and then we run the test, and then we see that it fails. In some cases, it fails. Okay, so in the case of frequency underflow, frequency overshoot, frequency error, for different types of faults, also it has failed. So you can go there and see what's going on, make the modifications that you understand that is important. So this is quite interesting. At the beginning, I was a little bit skeptical of the test-driven design, but with time, I learned that it reveals, something that might be hidden, that you only would find in the field after months or years of operation. So running this test extensively, so it can easily review what are the good points or weak points, strong points of a given controller. For here, in this case, we are testing a second-order generalized controller with a frequency locked loop. So we have available there in the site Kalman filter for synchronization algorithm. We have synchronous frames, PLL with positive sequence extraction, and so on. There is a couple of alternatives that you can consider for the synchronization algorithm for grid, especially for grid following converters. We also have a course on current control. Okay, there is, again, when you are going to implement a controller, there is different alternative. We consider single and multiple resonant in alpha beta coordinates, deadbeat controllers. Deadbeat controller is formulated as state feedback. And then more recently, we are testing module predictive control for grid-tied converter. So so again, the idea is the same. We put the code inside of C routine, and then we have this test-driven design that automated the generator report, where showing the points where the controller in this case didn't pass the threshold that we have set. So here is one example of a single resonant controller. This is a steady state tracking error where during a fault type A with the 90-degree. This is 90-degree phase jump here. It doesn't matter because we are looking at the steady state. Of course, if something goes wrong, you can go there and see the waveforms. See another example of these colored tables. We have this, how well this controller can reject the harmonic from the grid. So we have this also, this is each one of those points and one simulation that have been carried out. Okay, the last module, we have this modulation also in the outer controllers, but we are gonna jump to this last module that we have prepared that is regarding a primary control. So basic motivation is that when you have a microgrid, especially when they are operating in the island mode, and if there is more than one energy storage system or DR that have providing active power, you have to have a sharing of active power among them. So primary controller is one way to do this power sharing. So it's basically, we can divide these two classes of grid-tied converter, that is grid following and grid forming. So grid forming, it starts with the idea is that, well, how can I put this in a simple way? Grid forming inverters, it can make the grid in terms of voltage and frequency, and also share power among the different DRs that are connected to this microgrid. So basically, that doesn't rely on the synchronization algorithm. You might have one synchronization for connection, but conceptually doesn't need to have one synchronization algorithm. The primary controller provide information of voltage and frequency, similar as a synchronous machine. So the initial idea is that let's emulate, so introduce this inertia of a synchronous machine on inverters. Of course, that the design of the DC surge, it's very important because it does have to have energy stored if you want to provide frequency support, for instance, when operating with the one inductive grid. So the idea is the same, to recognize the differences between the main type of primary controllers, that the droop synchronous, virtual synchronous machines, and also the dispatchable virtual oscillators. There is another approach over there. Also, we encourage people to try this test-driven design and see whether it behaves better or not in different operating conditions. Also, the idea of this course is to provide design methodologies for the main parameters of this primary controllers. The idea is to get familiar with the test-driven design, that make this fair comparison, or at least try to make a fair comparison among these different primary controllers. The main point is what's good, what's bad about the different alternatives, how they behave, how they behave during short circuit, for instance, how they behave when returning from the short circuit, when the short circuit is cleared and the voltage has to recover, how these controllers behave on these situations. Yeah, this is basically we gather information for both the steady state and also the small signal behavior of this droop virtual synchronous machine, the transient, and then here is the virtual synchronous machine. I'm going to pass these ones, and also we show from the test-driven design how they behave in terms of frequency support, voltage support. We see that the droop with two integrator, in the case of frequency support and voltage support, he passed 100% of the test. Okay, so we have two alternatives here for the virtual synchronous generator, either with the feedback of the reactive power on the gap or the feedback of the reactive power on the point of common coupling. We see that the last one has a better result. And then we have this transition test, and what's happened when we have an unplanned island. We see that the dispatchable virtual oscillator is one of the best one on this test. And then we move to this island mode test, when you have operation with nonlinear load, with linear load, and then we have short circuit, two short circuits. We consider one short circuit of 50 milliseconds, another one of 200 milliseconds, and we see that, for our surprise, that the conventional droop is one of the has the best performance in terms of short circuit. Okay, basically what I had today is these ones. Back to you, Fernanda.
Thank you very much, Professor Humberto, for your very nice presentation on the test-driven design. And so now we have that our three speakers have presented their works, the research topics, and we can move on to the question and answers. So I really encourage the attendees, if you have any questions, please, you can make them through the chat, the Zoom chat or the YouTube chat, and we can proceed with the discussions. So we don't have yet any questions in the Zoom chat, so I will begin this Q&A session. And one thing that you have mentioned is that we have grid codes always evolving and changing, and it is expected that the inverters comply with some grid support functionalities more and more as we have more penetration of wind power and solar power. So I would like to know, both from the industrial and academic point of view, which is the impact of this grid code is always changing. How does industry deal with this challenge, let's say, so of keep their inverters up to date with this challenging grid codes and these new functionalities that are demanded by the utilities? And we know that pre-certification is a way to accelerate this design. Also, test-driven design can help us develop and test controllers for grid-tied inverters. So I would like all of you, if possible, to give some overview on what you think about this issue of the grid codes and the necessity to keep the inverters always up to date with these grid codes.
Well, if I may start first, I will mention our real-life experience. At AIT, we are also running a third-party certification lab for PV and battery energy storage and also drive converters, which are grid connected up to 1 megawatt and 1500 volts. So we test everything from small single phase up to utility scale or large power converters. And what we've seen in past that our industrial partners or customers had to come to a lab several times. And this, in many cases, became a quite big burden or quite expensive for everyone involved in this whole process. On our end as a lab, we've seen customers that simply after some time being not able to pass this grid codes which are evolving, they simply in some cases completely gave up, or they just were not able to fulfill, or they were faced with huge expenses related to that. So then several years ago, we introduced a concept of C-Hill pre-certification, which means that we offer to our customers that if we develop a C-Hill model and we test it within a Hill environment, then their certification process will become streamlined. And we demonstrated that concept to some leading industry partners, and we were very pleased that some of our partners adopted this concept. And in that way, that at the end, they witnessed that if it is not tested or pre-certified, then it is like not being tested at all. And that at the end, testing in a lab was completely streamlined up to that level that in past they had to come several times to our lab. At the end, they would just send, especially during Corona time, they will just send converters and that's it. And then we will test for them, and they will just witness test via video links, and new software upgrades or firmware upgrades would be sent to us. And on the other hand, they would test these firmware candidates on their C-Hill setups. So definitely, this is one of the ways to actually mitigate this challenge of evolving standards, if I may say.
Thank you very much for your answer. I would like to ask if any other of our guests would like to make a comment or add something.
Maybe I can share our experience as well. It's really a trick business when you have to deal with moving targets in terms of the requirements. In our case, as an inverter manufacturer, the way we have been tackling this is really by mapping first what are the main grid codes in the markets that we want to sell the inverter. And we have to carefully study them, find the commonalities, and what are the specifics. And the next step is usually how you plan to implement those functionalities that will meet the requirements. And that's usually a two-step process at least. The first one is we try to build the software or structure the software to be as modular as possible, because that is what enables us to adapt quickly when there are changes. And the subsequent step is actually starting planning how you are going to test against the requirements, because if something has changed drastically, like it usually happens, then you have to be prepared, and you have to start this dialogue with what is the agents that you want to certify your inverter. And usually, let's say, it's not like what's strictly reading on paper. You have to start this dialogue with the certification agency and make sure that both parties are on the same page, meaning they agree how this test is going to be performed. Because if you try to design without this feedback from the agency, you usually miss, or you may miss, big things. And that's what I call risk business in this specific regard. But usually this dialogue goes very well, and the product development can adapt quickly. But of course, we cannot meet all requirements from all markets. So usually you have to do this initial research. What are the main markets you want to target your product, and study the requirements. That has been the usual approach. And I see here on the Q&A box, there is a question, very good one, related, for example, can we use just a hue for validating the performance of the drive? And the typical answer would be no, because there are things that you need to prove by doing actual tests with the hardware. But fortunately, it has been a very consistent trend that we can use the hue to validate, especially functional tests. For example, when you have abnormal grid conditions and your drive is expected to disconnect from the grid within a certain window of time. And those types of tests that are relatively easy in terms of surviving or performing well the test, those we have been successfully proved to the certification agencies through hue testing. And they are usually very open to that type of approach. But it's something that really relies on the performance of the hardware, then the answer will probably be no. And we don't even spend time trying to convince the agents that, yeah, we can meet the requirement on a hue environment. That has been some of our experience.
Thank you very much, Leandro, for your very nice answer. I will ask again if anyone of our speakers want to complement this question, make any more comments.
This is a really nice discussion. I just wanted to bring up a precedent. So actually, aerospace industry has a really nice precedent. Aerospace industry, software is a safety critical component. And for example, when you are testing and validating, certifying certain control software upgrades and updates in aerospace industry, it's basically a requirement that documentation comprises both hardware in the loop testing and real hardware testing. And what that really means in practical terms is that they have figured out that real hardware testing can only get you so far. If you are testing a critical control component of a jet engine, it's really difficult to get it into all operating conditions. And these are the operating points that they like to supplement with hardware in the loop simulation results. So really, to get certified, you have to do both. And the key piece that I guess is kind of implicit there is that there is a process of validating the model. So model validation is kind of like a key piece to get hill simulation accepted, for example, in aerospace industry. So first you have to build a model. You have to verify that your model is actually doing a good job in specific set of operating points. Once the model is validated, then you can actually use this for specific types of results. And I think this is something that, you know, we are trying to help out in this process to kind of bring the same kind of thinking and same process to you know, let's say grid-tied converters, which unfortunately in many applications are not safety critical, but they can be actually mission critical. And that being said, I would like to ask Zoran. Zoran, you know better. I think in German code BDW there is a precedent for certain grid-tied converters to verify the model. Can you comment on this?
Exactly. This is a case with the medium voltage certification, where it is required to produce also a model of controls of medium voltage converter, and to this date it is sufficient to do let's say offline simulation model for this purpose. But I would say that to, let's say, add on to what you mentioned, Ivan, we are seeing a need to perhaps certify not just control, but the whole digital twin, not just the model, but the digital twin. The digital twin comprises of really a control and power stage simulator, or whole digital twin of the power converter, including lab, including measurement, and all of that. And the idea is actually to invite witness, or let's say two for VDEs or other to witness test, CSA to witness test, testing in the lab and in the parallel path of digital twin. And if this is validated against certain grid code, then digital twin may become actually, let's say, a reference to be used to basically validate everything against. Now this is this is all in a very early stage, but we are working toward that, and we think, especially in a change of the way how world is seeing a whole digitalization process, that this might be quite interesting. This doesn't mean that lab testing would be replaced, not at all. It is just that, for example, digital twin, high fidelity digital twin can be used to validate, for example, behavior models or some other models which are important, for example, for system integrators, which are not interested, for example, in some behavior under grid fault conditions, but just to validate whether this asset or DER would perform in their microgrid application the way they expect to. And how would they trust whether this model is actually accurate? If would they trust supplier or Schneider Electrics or Danfoss or SMAs or Typhoons? Not, of course not. They're going to go and look for independent third-party supplier, or let's say certifier, to say this model or this digital twin is actually certified or validated, if you wish.
That's a very interesting issue, and there is a question here. Actually, there are a few questions in the chat, but I will jump the previous question because Professor Lucas has made a question that is really specific to what you have just mentioned, Zoran, and he's asking how to validate the digital twin, how to assure no important defect is missing.
Well, the way is to actually do a side-by-side testing, and to actually the way how we do it in the lab, we use referent measurement equipment to test, let's say, to measure waveforms of current and voltages on input and output terminals of the device, which is a black box at this point of time, and to use very same measurement equipment to validate the model, and then to run a battery of tests in all conditions, and to then compare results.
Okay, thank you very much for answering. I don't know, Professor Umberto, if you want to make any comments on this. You are muted, Professor.
Sorry. Well, yeah, this is. I see that the using of HEAL is in the design process is it's mandatory this day, because you can validate your firmware in a safe environment. Okay, so the idea is whether or not you can use a model that to another purpose, for integration of a large, suppose if you want to do a microgrid, you have different devices, you have different even manufacturers. So how can you integrate this? Okay, so of course, if you have HEAL validated models, it will give confidence to the integrator to that there is a lesser chance of putting this thing together in real life and expect it to work. And so as the microgrid evolves, I think the HEAL certification of models is key to give this confidence for grid integrators. Basically what I have of comment.
Thank you very much. So I will move on to read the questions that have been sent into the chat and also in the Q&A.
Yeah, another comment. There is this. We have another Professor Yuto was my professor, was supervisor of Leandro de la Flora, and then he has one saying, there is no model. It's not exactly what he says, but I'm translating this. There is no model that's good enough for all purpose. Okay, so there will be phenomena that will not be captured for a model. There is so the idea is that you have to see what's the purpose of your simulation, what kind of time frame you are trying to capture. So if sometimes a simpler model is better if you're not interested in how the holes and electrons move inside of a switch of a silicon carbide switch. I don't want to know how they, I just want to see if it's switching open and closed. So we are not capturing this phenomenon, but we are capturing the PWM. We are capturing the saturation of the inductors. We are capturing how this will affect the harmonics into the grid. Maybe this is important. So the idea, the real challenge is how to have the simplest model, because the systems are becoming complex with different. Now, if you pick up a microgrid with 1,000 of converters, so you want to have a simplest model to capture the main phenomena. Still, I think there is a challenge on these ones. So what you should keep in the model in order to capture the behavior of this converter during recovering from a short circuit, for instance. If the short circuit is clear, the voltage will bring up. So the converter has saturated inside, each one saturated their own way, the controllers and so on. So this is not easy, but anyway, it's something to be addressed in the future.
I agree, Professor Umberto. I think this is really important point. I mean, I guess what, in my mind, there are three things. There is an actual model. Then there is this verification and validation procedure, how you are verifying / validating that model. And then kind of implicitly there is this domain of validity. As you said, every model is good for something and bad for something else. Yeah? So I think it's really important to understand what's the domain of applicability or validity of that specific model. And you also have to prove that, you know, what does it mean it's good enough in this given domain of validity. And it's really interesting. I mean, we see that kind of as you are moving from, let's say, inverter manufacturers to, let's say, system integrators that take these inverters into battery storage system, their model requirements are changing. So inverter manufacturer is really worried about testing all these nitty-gritty details in terms of, you know, high performance, you know, fault injections, grid disturbances, weak grids, low voltage write-throughs. They really want to make sure that it performs under all possible conditions. But now that model, when it ends up in a system integrator that says, for example, that puts together battery energy storage system, their appetite for kind of testing and validating the, you know, specific inverter details is kind of coming down. They are now really more worried about, you know, specific communication aspects. How does this model communicates with higher level battery energy storage controller? You know, how does it interact with the grid, but on a slower time scale? So it's really interesting. I mean, they are requiring specific things from specific models. I believe that in the end we could connect all of these models. You know, there is a physical reality, that's the ultimate truth, yeah? And then there is some data that we obtain from the, you know, lab measurements, and then, you know, we can use that to kind of like validate certain aspects of the model and kind of have this chain of different connected models that are validated against each other, and then basically kind of extend the domain of validity for these different connected models. Over.
Amy.
Leandro, you're muted.
Oh, sorry, I was unmuted and I muted myself. So basically, I just wanted to add a practical example to what Professor Hilton has commented out. Is really a very good point that there is no solution that will fit all needs when it comes to modeling. And the practical example I can share is really when I was in the aerospace industry. It was such a valuable experience because it introduced me to a quite demanding level of testing and requirements and documentation that I was not used to. And what I take from the experience is really that it's not the model that's driving the requirements, it's the other way around. And I remember one specific case, the customer was quite fine with us providing different models with different levels of details and fidelity, because at one hand, they wanted a model that was proven that the design was meeting the requirements. And then you are talking about reproducing phenomena that happens in the tens of microseconds. But on the other hand, they also needed real-time models that they could run on the test rigs to validate the, let's say, the system level functionality. In that case, 1 millisecond was fair enough and good enough, I would say. And we had all this work of creating these models and maintaining them according to the customer's purpose or intended use of these models. So it's just a practical example I wanted to share, because I see there's some comments on the chat window about the validity of these models, and it's really a big topic, and there is no simple answer. We have to accommodate according to what you want to replicate and prove.
Thank you very much, Leandro. And I will read a question from Professor José Renes. That's the same question that he asked for Ivan on the previous session, and it really goes into this discussion of the model. So I will read the question here. So he wrote, I repeat the question, which I did for Dr. Ivan Silanovic, to hear the opinion of you about that. Our digital simulators, emulators, view systems are model-based systems. how to meet the best and adequate model, good accuracy and fidelity for our studies, analysis and design, before to perform the experimental validation or to know these realities, when there are different subsystems, scenarios, powers, and scales, with high degree of complexity, including different scales, huge challenges, just with confidence, validated digital platforms we can use for our designs. Are there other ways to do this? So I think you have already talked a little bit about this, and if you want to include any more comments on this regard, please feel free to share with us.
Yeah,
any one of you, if you want to talk.
I can. Sorry, I was talking before. Maybe other colleagues can talk first.
Go ahead, Leandro. Go ahead.
Okay. Yeah, I think Professor Hennis is bringing up very good points, and there is no simple answer in my opinion, because let me give you one example. When we have to design a heat sink or the cooling system for an IGBT, then you are interested in certain dynamics that are in the microsecond range, and then you need a lot of details, especially because you want to see the real commutation of the switch, right? And that is, I mean, that has been changed over the years, but it's not as simple as we wanted to do that in real time, right? So still to this day, we support a lot of offline models that can give us that level of accuracy, but not the speed that we wish. But we are seeing, like, even when we look at Typhoon products, that has been helping a lot, because the tendency we see, or the trend, is these types of simulations with high complexity, very low time constants, they will eventually be occurring in the real-time environment, and that will speed up a lot. That's what I had to add.
So if anybody wants to add some comments, please feel free.
If I may say, for grid-connected converters, which are, say, switching up to 40-50 kilohertz, with the current state of technology, with Hill simulators, which are based on FPGA technology. There are some which are based also on DSP technology, and at AIT, we have to stay impartial, and we have all kinds of digital Hill simulators. For FPGA-based Hill simulators, we can see with their high fidelity or rate step, basically harmonics up to 50th harmonics and stuff like that. So it's fidelity or match between, let's say, what we see in a lab and what we see in C-Hill simulations is very high. If we talk about some resonant behavior, or we talk about high frequency switching to 50 kilohertz and up, then this is not the case anymore. This is not to say that there are no other ways around. For example, to clock down simulation and etc., and then to basically clock down or slow down simulation by order of magnitude, and then it's not a real-time simulation, but it's near a real-time simulation, and we may achieve similar results. So it depends on application, depending on the need, but let's say for majority of standard application, power converter applications with silicon and silicon carbide devices, current state of technology on Hill real-time simulators based on FPGA technology, we get really satisfactory results.
Any more comments from our speakers? Okay, so we have more questions in our chat. So we have reached the supposed end of the session, but as we have more questions, I would like to ask you, our speakers, if you mind if we continue with this Q&A session. Is that fine for you?
I'm okay.
I'm okay too.
I'm okay too.
Me too.
So I will read the question that we have here. Some of them maybe you have already answered some parts, but I will read just for you to know them. So the first one in the order in which they arrived is this one. It was made by Ricardo Bortolini, and he's saying, how is the development of standards to accept Hill testing as a compliance testing method with the same value of a conventional laboratory test? Will Hill testing replace the conventional laboratory testing for final products like PV inverters? In what areas it is more probable, for example, high power levels, lower electronics, power segments, and which are the challenges to achieve this?
Maybe I can give I think we talked about this a lot. I mean, Power Lab is never going to be replaced. I mean, Power Lab has its own space. The way we see this, for example, from hardware in the loop manufacturer point of view, is that hardware in the loop belongs kind of like square into V&V, verification and validation of the control software and firmware for power electronics and microgrids. So what that means is that it has its central role in testing and validating, and also being used in the development phase when you don't actually have the actual power stage. So this is kind of like when you don't have actual power stage, you're using hardware in the loop as a tool, to help you quickly, kind of like early V&V, early verification and validation, to test out your algorithm, and you have your sandbox. Then once this is done, basically you're moving to second phase, which is actually rigorous verification and validation of your control software, whether it's a component or a system. And in the end, you do have to test the final system. These two are really complementary. How much of the testing in the lab you can offload to this much more much easier to use and less expensive hardware in the loop setup, and how much of these results will be accepted by certifying bodies. I think it's just a process. We have a lot of precedents, but it's one of these things that you have to kind of convince people that you have validated your models. This is really good, and there are certain advantages to that. So I think it's a process. In the end, you have to plug your converter and test it in multiple operating conditions, because it's just a natural way of kind of going from component to system testing, as you're increasing the complexity. So that's kind of how I see this.
Any more comments? Anything that you would like to add? Okay, let's see the other questions that we have here. Maybe it's this question is also kind of covered by what you have discussed already, but I'm going to read this anyway. It was made by João Pedro Cipriani, and he's saying, in this context, do you all think we are moving to a new standard, design requirements to design itself, to Hill validation, to product development, to product validation for most power electronics products, or just these mission critical applications?
I'm gonna make a comment here. I think we power electronics designers are under pressure to deliver product to the market as soon as possible. So, of course, in order to do so, we have to meet the requirements of the grid codes and so on. Hill validation gives the designer the confidence that the real test in the lab will probably be fine. as long as the noise level is compactable and the powered circuit is working properly. So there is, you can work in a safe environment. As Leandro de la Flora showed her picture in the office testing a medium voltage converter from his desk. He understand, I mean the firmware of the converter. So he's pretty confident over there that can do everything and make sure that everything is fine before it goes to the real life. I think this is no way around. I cannot think to do a design today without having a hill test. You understand? So it's too dangerous. It's too maybe too cost effective. So so it's better to have everything working in a control environment before you set the circuit in the real power level that it has to handle. So that's one way of the answer the question that he made. I think the hill validation should be there. You understand? Even though it's not mandatory. So for it is there because it's a part of the process, already part of the process. Whether or not the bodies, the agency will accept this as a certification test is something else. You know, it's another level. Okay. Contribute to the discussion.
Yeah, I'll just add a quick comment. So because of the pandemic today, it's even more important because that picture was taken before the pandemic, and today I work from home, but I can still access that equipment and do all the simulations from my home, and that's so helpful. I mean, if we didn't have this type of approach, we would still be in need to be everyday presence in the office. So it could be anywhere in the world today with internet access. So, I don't see, this is a kind of irreversible process. It's making everything easier. Yeah. And the company, I can tell, Danfoss, more than 10 years ago, started this path by designing our own hill systems, and a lot of was invested, and we reached a certain maturity level. But after some time, it became clear that, well, this is not our main business, right? We are designing inverters. We're not designing hill systems, but those systems were in the early days extremely helpful. And we are glad now that the test equipment industry is picking up and developing this nice system. That's extremely helpful.
Yeah, thanks, Leandro. This is really nice comment. This is exactly kind of how we saw this. When we started Typhoon, basically our biggest competitor was a lab on one hand and in-house built hardware in the loop systems. And, you know, certain companies decided to build, you know, homegrown hardware in the loop test systems because there was nothing in the market that worked for them. And, you know, we saw an opportunity and we developed and then put like huge amount of effort to make hardware in the loop as accessible and easy to use and as inexpensive as possible. So now from our perspective, we see that companies that care significantly about the cost, reducing time to market, improving quality, and, you know, that have limited, you know, engineering staff and really want to be agile, they are adopting hardware in the loop as an integral part of the process, whether it's mandated or not. So these are kind of the main drivers, and companies are recognizing this. Can you do it without? Sure, you can do it, but it will take you, you know, so much longer. You know, it will cost you so much more time. Quality will be questionable, and the amount of staff also that you need to have, you know, in order to supplant, you know, the lack of hardware in the loop test bed and processes and test automation is huge. So.
Yeah, I'd like to make a comment here. There is, as we are talking, actually, if we are dealing with the design of 5 watts power supply, you might rely on the conventional approach without doing any hardware in the loop, you understand? Because probably you're going to do PSPICE simulation and do some prototyping. And then as we move up in power, okay, I think there is no, I think it's more valid this statement that there will be no power electronic design without a Hill validation. I don't know if you agree with that, Ivan.
I agree, and that kind of goes back to that kind of cost issue. It's more, it's less expensive to do testing with lower power. So then basically the benefit is kind of like lower. The biggest benefit really is in, higher power and, designs, but, also as kind of availability and fidelity and kind of the whole process is evolving. I also see that, this kind of boundary between, low power and, higher power designs or no hill and hill designs is also changing. I mean, it used to be, I don't know, rule of thumb, if you are doing 10 kilowatts or more, it makes a lot of sense, but then below not. But now we are seeing, even a kilowatt and below kilowatt type of power level converters and controls for them being tested with hill, simply because it also brings some process, reduces the cost, also brings some discipline in terms of how you approach this systematically, and so that there are also these other kind of benefits that are not directly related to design, but they're also kind of like more kind of like model-based benefits of doing things in the model-based environment.
Thank you very much, Ivan, Professor Humberto. Any more comments on this question? Okay, so I'll read another question that we have on the chat that was made by Henrique Manhago, and he's writing, question for Zora. Regarding the testing process from Hill to the lab, the Hill setup is a very safe environment for automating certification tests. Do you also automate the lab certification? If so, are the tests from Hill and the lab shared, use the same tools, or they are developed independently?
Well, we have two examples. One example is that same tools, automation test tools, are concurrently developed for design validation testing in a lab and design validation testing on Hill using Python scripting language. But the other example is where existing testing scripts were available for which were developed for decades by some industry partners, and they were written in C#, for example, but they were with certain type of converters, basically translated or interpreted in Python. So at the end, same tool is used for lab testing and for legacy developed test automation hardware. Literally, the difference is whether you choose driver for, let's say, certain power amplifier or power supply, or on one end, or for API of certain Hill emulator.
Thank you very much for your answer. I don't know if anybody else wants to make a comment on this question, even though it was specifically for Zoran. Okay, so I'll read another question that we have. It's from Professor Lucas Bellinazzo, and he's saying, which are the challenges for the development of Hill simulations and automated tests using Hill with the increase in the switching frequency of power converters, considering emerging semiconductor technologies, such as silicon carbide, that allow switching frequencies up to hundreds of kilohertz?
Well, I can briefly, yeah, I mean, it's always a challenge. trying to keep fidelity as high as it is needed for specific task of testing and validating control firmware. And so basically what I guess on our side, what we have been doing is kind of two things. So on one hand, it's reducing the simulation time step. And then on the other hand, it's also improving the models, because you can also, for testing control purposes, you can also improve model fidelity while still not necessarily reducing the time step. So for example, just to give an example, now we have some really nice results with dual active bridge with a very high fidelity going up to 300 kilohertz switching frequency, and then similarly with some also with some resonant some other resonant topologies as well, 250 to 300 kilohertz, using the time steps down to 250 nanoseconds, but also doing some other kind of clever things when we are developing models. So we kind of keep pushing that envelope, trying to reduce the time step and improve the models, and that's what we do. And then Zoran also mentioned at some point, if you can't do it, then you can also play some other games like frequency scaling, so that you're scaling frequency basically of the controller clock, and then in the discrete domain, basically you are kind of doing the same thing. So it's a little bit of cheating, but you can still get a really nice process and process flow for validating the firmware, and that's also available for that.
Thank you very much, Ivan. I'd like to ask if anybody else from our speakers want to make a comment on this.
May I ask a question to Ivan?
Sure.
So in the offline simulations, like in the MathWorks product, we can choose between among a number of solvers to get the fidelity that we need. And that gives us a lot of flexibility, especially when we can do variable step time simulations. And I always wondered how you guys are improving the fidelity of the models to run in real time. And of course, you're not going to disclose anything that you cannot, but my biggest question is, in the offline simulation, when you have a zero crossing event, you can basically reduce the step and get the details that you want. How are you guys tackling that with the real-time simulations?
Yeah, so this is a good question. Yeah, so our constraint, it cannot be a variable time step, so it has to be fixed time step, whatever it is. Then second thing is we cannot really iterate. That's another thing that offline simulators can do. When they hit a problem, they go back, reduce the time step. We have to finish our computation within finite time, and that's our upper bound, how much we can take to compute this thing. Now, that being said, we can play a couple of games to achieve that fidelity. So one thing that we can do is we can analyze the model ahead of time, and that's usually what offline simulators don't do. So you analyze the model ahead of time, and then you know what you are dealing with. I kind of compare this with skiing downhill. Yeah, you can ski downhill by first knowing your GPS map and then figuring out exactly how you want to go down because you do some analysis before, or you say like, okay, well, I have no idea, I'm just going downhill, and then I'm kind of like, I see a little bit further ahead, and then I'm moving as I go, and if I get stuck, I walk back, and so on. So we do a lot of analysis ahead of time, and then the other thing what we do is we also trade some flexibility that offline simulators have for fidelity. Yeah? So what I mean by that is like you can kind of limit the flexibility of what you can do with your simulator in order to gain more speed. So simply your simulator will not be able to simulate everything in every model and every system, but for specific systems, I don't know how to explain this, but there are certain there are certain trade-offs that you can do so that, you develop better models, but, they're not as applicable as an offline simulator. So that's kind of how we approach that. And then at some point there are limits to the physics. You can also do a lot of prediction as well. So when it comes to zero crossing, you can actually run a prediction in parallel as well and figure out when is that going to happen and so on.
Right. That sounds great. But sorry, I will insist on the question. Is it fair to just assume that at some point these boxes will have so much computation power capability that the basic solution will be, well, just reduce the time step as much as this hardware allows you to, and that will take care of everything? How do you see the trend moving forward in the future?
Yeah, so one thing is that we are relying on the semiconductor industry, that they're continuously speeding up the computational platform, which in our case is an FPGA. Actually, it's an FPGA ARM SoC. So this is something that is kind of like industry is driving. There are these big players, and then industry is driving the platform to be able to operate at faster and faster clock, but also to have more and more computational fabric. So we are always leveraging this trend to kind of keep reducing the step and then keep increasing the computational complexity of the model, because simply it can crunch the numbers. And we are also improving on our side. Also, we are improving algorithms and also improving some of these models to be more computationally efficient. Mm-hmm. That's kind of the trick. Yeah? But now at the moment we are at 250 nanoseconds, and we are seeing that we can cover a pretty good large space of applications that the industry is requiring from us today. So, but as I said, keep pushing.
Right. Thank you.
If I may comment on the same topic, well, it's faster devices not only require a faster simulation on one end, but also faster controllers. And I think there is quite some, let's say, latency in controller developments. Majority industrial controllers are based on DSP platforms, not on FPGA platforms yet today. And also know-how is in DSP software, C code, C++ code development, not in FPGA, VHDL, or whatever controls development so much. So that is also impeding real industrial applications of faster devices beyond 250 kilohertz, I would say.
Thank you very much for all your comments. This is a very nice discussion. Really, really interesting. We are moving towards this faster and faster controllers and inverters, and this is a really important issue to be addressed. Now we have one final question in the chat that was made by Henrique Manhago while we were talking. Yes, Professor, please go ahead.
What Zorik mentioned about the FPGA and DSP, and then it happens that we at this moment we have there in the lab one team that is testing one 300 kilowatt PV inverter. He is using Typhoon Hill to test the firmware, and all the controllers are implemented in FPGA. And then since there is a interleaved three-phase rectifier, DC-DC converter, I would say, interleaved DC-DC converter and interleaved three-phase inverter, there is a lot of inner circulating current loops, and also this MPPT, voltage control loop, and so on. And I was impressed that he was able to design all the controllers in continuous time domain, and then implemented with a sampling frequency of 60 kilohertz. You understand? So even though that it has a very large, I would say, not very large compared to the one that Leandro is addressing, but very relatively complex converter, the idea to use FPGA made it possible to design in continuous time domain, and you have a fairly good response. You understand? So I think FPGA implementation of the controllers will make life easier for these designers. Of course, as you push up the frequency, so the challenges, are still that you have to make the design in discrete time domain and so on.
Well, there is no doubt that this is going to a way to move forward, definitely with faster devices and in general higher switching frequencies. Our analysis showed that typical controls portion of application firmware is not more than 5% of overall product. Then we are seeing 95% of all these functionalities, like a LVRT. What do you do when there is a LVRT event? What do you do when there's a communication task, etc.? And at least for large companies, there is quite some inertia to move toward introduction of new technology for control purposes, and this may take time. Definitely the direction is to use FPGAs for control as well. Yes.
The way that I see now, maybe I change in the future, but the way that I see it, FPGA it is definitely a strong candidate for the implementation for control, new converters and controls that run at 50 kilohertz, 100 kilohertz. But still, you might have another DSP over there just to do the rings and bells, that are required to make the converter work. Still some development in C language or another language, and then have the controllers in a lower level implemented in FPGA. I don't know if you share the same opinion with me.
Most definitely, and this is, let's say, future which is coming.
Thanks for all these very interesting comments. This is a very nice discussion. So I will read the last question in the chat that was made by Henrique Manhago while we were talking about the model. So maybe this question has been already answered, but I'll read it anyway if you want to make any further comments. So he's saying, regarding these models, do you see the use of a generic model where you can parameterize it, or a specific model for each O&M device? Will there be requirements to be able to run it in real time, or mostly using offline simulations?
Well, may I comment about the first question? I think there will be more and more models driven by standards, meaning, like it was mentioned in the discussion before, we have this German grid codes that require the inverter supplier, for example, to develop a model that represents the main functionalities of the inverter from the grid point of view. And I think those will happen more and more in different industries or segments of the same industry. But I don't think there will be one size fits all, meaning one type of modeling approach that will reply or answer all types of demands. That doesn't sound practical to me, and this experience has shown that it is not so practical. That's the comment.
So, any more comments on this question? Okay, we have one attendee with the raised hand, so I really don't know how to make this work. So maybe I just need to, allow to talk. So Rodrigo Oliveira, you are allowed to talk.
He has to mute his mic.
Please, Rodrigo, can you unmute your microphone? Oh, I don't know what happened. Rodrigo Oliveira Salvati, are you there? Can you unmute your microphone and ask your question? Okay, I don't know what's going on, why he's not asking the question.
Maybe you scared him, Fernando.
Let me turn off my camera, then maybe I stop scaring people out.
I don't think that there is a mic beside his name, so I don't think he has a mic.
Yes, it doesn't have it.
You have to send a.
But I'm not available to open his mic because there is no mic symbol by the side of his name.
Okay.
Yeah.
So, Fernando, I believe the audience can open their own mic. The moderation has to do it. The moderator has to open the mic. I don't know who is the moderator. If you are the moderator or Soft Alisa is the moderator.
I'm just moderating the session itself, but in my system here, I don't have the option to unmute him. There is no microphone by the side of his name here, so I cannot unmute him myself.
Yeah, it says he didn't join with a microphone.
Okay, so maybe Rodrigo Oliveira, if you want to ask your question through the chat, that's better. Okay, so we don't have more questions in the chat. We don't have also questions on YouTube. So I think that basically this is it. And it's really nice that we had a longer discussion than expected. This means that everybody was interested in this talk. And I myself found it really interesting that you were able to share with us all this knowledge and these interesting issues about these very important topics for us that are working on power electronics and microgrids and all these other important applications. So we would like to thank you very much for joining us on this panel discussion, and it was really, really interesting, and really thank you for sharing your experience, your time, and your works with us today.
Okay, thank you for the invitation.
Thank you so much.
To talk to you. Have a nice weekend over there.
Thank you.
Thank you. Pleasure
Thank
was
you.
mine, and have a good rest of the weekend.
Yeah.
See you
Let's
next
keep in
time.
touch. Come on.
Thank you, guys.
In
Thanks.
touch.
Bye-bye.
Bye.
Thank you so much.
Bye.
Very nice discussion. I appreciate it.